All right, so the topic for today is binary heaps. So let me change my microphone and change the, all right. So the aim really is, we talked about the list ADT. And now let's talk about another ADT called the priority queue. So the way you think about a priority queue is objects have a priority, and this is usually in the field that we will call key. So each object has a key, or it's a priority. And so this, now I'm giving you the ADT, which is the specification. The specification is we'll have the operations insert. And the interesting operation that we will have, or the interesting series, are find max, which is return the object with highest priority, extract max, which is often just to delete the max, and another which would be increase the key. I'll explain this more, but essentially with a pointer to the object. So let me try to give an explanation of where you might want to do something like this. So if you look at, the assignment that I gave, with Shakespeare's words, one way of thinking about it is you have a stream of words coming in. So imagine, you could be, for example, a social media company. And so you have lots of words coming in every day. You could think of like this being all the tweets or all the texts or whatever, like some trending topics. So these could be words. And so at some point, as you're reading the words, you want to know what is, let's say, the trending topic right now. So you could think of this maybe being hashtags or words. And so as you see new words, you have to insert. So you're keeping track of the frequency of the words seen so far. Every time you see a word, you have to increase the frequency, or you have to insert if it's a new word. And you want to sort of find the max. You want to determine which is the word that was the most frequent so far. And then, of course, in this example, you don't need to extract the maximum, but you can come up with examples where you need to extract the maximum as well, which means you delete the maximum. You might say, okay, I'm going to look at everything that has been popular today. Now, once I'm going to remove that, because in whatever is left, I want to look at the new topics that are becoming popular. So I remove the maximum at a particular point. Right? So this is an example of where you might want to use a priority queue. Right? You want to keep track of trending topics or frequent words. So that is just one example where you want to also extract the maximum periodically. Another example usually given for priority queues is you can think of jobs that are being scheduled on a machine, and each job has a priority, and you want to find the job with the highest priority before you schedule it. So this could be even with processes running on your computer. So each process has a priority with which it goes into, with which it needs to be processed. So you can implement these. You can implement the priority queue using the data structures that we know and love. So let's just look at doing it with a linked list, with a sorted array, and see what kinds of runtimes we get. So again, I'm going to draw this table that we've seen where we have a data structure. We have a data structure. So we can look at the linked list, and we can look at a sorted array. Now let's list out the operations that we want. So we have the insert. We have the find max. We have an extract max, which is deleting the max. And then we'll have an increase key with a pointer to the object. So we can assume that, right? So all of these, the linked list and the sort array, would give implementations of this. So as we discuss now, I'm going to now put the running time here. This is theta of 1. We can insert in theta of 1. But how long does it take to find the maximum? Right? How long would it take to find the maximum? Right? So to find the maximum, you can just do one pass over the linked list. That will give you theta of n. Now, let's say how long will it take to extract the maximum with a pointer? Suppose you have a pointer to the maximum, then deleting the maximum is going to be theta of 1 with appropriate pointers. And increase key is also theta of 1. Now, in a sorted array, what's going to change? In a sorted array, what's going to change? How long does insert take? How long does insert take in a sorted array? Right? Insert is now will be theta of n. What about find max? Okay, so now I'm going to ask this question. What is the running time of find max? And here are the options. Your options are theta of 1. Is it theta of n? Or is the question confusing? Question confusing, or you're not sure. Okay, so I'm going to launch the poll now. Right? So, how long does it take to find the maximum? Is it theta of 1? Is it theta of n? Or is the question confusing? You're not sure. And when I say sorted array, you can think of sorting it increasing or decreasing, whichever is convenient for you. Whichever is convenient. Do whatever you want to make things the most efficient. Okay, so most of you, I think, do see the answer that it's theta of 1. Why? Why is it theta of 1? Does someone want to sort of hazard a guess the answer?
Because the max is either going to be at the end or the beginning.
At the end or the beginning, exactly. And if you keep it in decreasing order, then it's just going to be the beginning. So it's easy. What about extract max? Now this one has to be a little careful. So maybe what you should do is if you keep it in decreasing order, then actually you can do it in theta of 1, because then you just keep a pointer to the last element. The last element will be the maximum, and then you can easily delete the last element in a sorted list, right? By just shifting the size. What about increasing the key? So the way to think about this is, suppose I have an array of numbers and I need to keep it sorted. And I go ahead and I increase the key. Now, how long does the increase key operation take? So you have a pointer to the object, meaning that you have the index of the element, but you want to increase the key. All right, so I'm going to relaunch the poll. How long will it take? Okay. Okay, so there's a little bit more confusion on this answer. So think about this. Suppose you wanted to increase the key, increase the value in the 0th element of the array, and you want to increase it to become the largest, because you want to increase it to, you can increase it to anything, increase it to the largest number. Then all of these elements, everything here is going to have to shift back by 1. Right? So you'll need to write a for loop to shift everything, and that is also going to create a theta of n. Any questions about this? Now, I recommend you redo this exercise with an unsorted array, just so that you understand what is going on. Now, observe that the nice thing about the linked list is that the insert is really cheap. The nice thing about the sorted array is the find max is cheap. But, they're sort of flipped. This is theta of 1 and theta of n, and this is theta of n and theta of 1. Can we get the best of both worlds? Can we actually do an insert and a find max both in theta of 1? Like that would be like the best of both worlds. And indeed, a binary heap comes close. So what we can get is actually the insert.
Theta of n.
I'm sorry?
Someone wanted to elaborate about why it's big theta of n. I'm supposing on an increased key with the sorted array.
To increase the key in a sorted array, right? So because if you wanted to increase, so let's just say you have a sorted array and you want to increase the value of the 0th element. And let's just say this is sorted in, increasing order. So if you increase this element, you have to maintain the fact that it is sorted. So just by you cannot, okay, so let's just give an example. You cannot increase this number and leave it where it is, because then the array would not be sorted any longer. To maintain the fact that it is sorted, you have to move this element to the end, which means that all of these intermediate elements would have to move one step back. And this would require a for loop that is going to run through the entire array. So in the worst case, an increased key can be will be linear time.
To clarify, we're always looking at worst case, yeah?
We're always looking at worst case, right? Whenever one talks about running time, one is looking at the worst case running time. Okay, so in a binary heap, the insert becomes log n. The find max is actually going to be theta of 1. The extract max is going to become theta of log n. And the increase key is also going to be theta of log n. So what we can get is we can get essentially all the operations to be in logarithmic time, right? So it's a very clever data structure, which gets the best of both cases, sort of almost. Instead of theta of 1, you get theta of log n. But as we discussed last time, theta of log n is really small, right? If n is 1,000,000, then log of 1,000,000 is something like 20. So you do 20 operations as opposed to doing 1,000,000 operations. And so our task for today is to study the data structure, the binary heap. All right. So here is what is, I think, extremely clever about a binary heap, but tends to confuse students quite a bit. So a binary heap is just an array of objects. So it's just an array, but we interpret the array as a tree, actually as a binary tree. Okay, so let me explain. So here's my array. So I'm just maintaining an array of objects. Conventionally, and this will be convenient for a lot of indexing, a of 0 will be empty. So I'm actually not going to store anything over there. I'm just going to keep it empty. And so my objects are really going to start from A1, A2, so on and so forth. And the reason for doing that is that you'll see that a lot of the coding and the indexing becomes a lot easier. And we'll maintain size to be the largest index. So size is the largest index, storing something in the binary heap. I want to emphasize that I'm not going to deal with like memory allocation issues here, which I did say, like, one of the benefits of a linked list is, you don't have to do this sort of dynamic you can allocate just exactly what memory you need. Here I'm using an array, so obviously memory issues will play a role, and I'm not going to get into the details of that. So you can assume you're using some kind of dynamic array of some form. Okay, but now here's the important thing. How are we going to interpret this as a tree? We are going to treat A1 to be the root. And A1 is going to have two children, A2 and A3. And A2 is going to have children A4, A5. A3 is going to have children A6 and A7, so on and so forth. I am not maintaining pointers, but I'm just going to imagine, the code is going to imagine that this is actually a tree, even though it is stored just as a normal array. Right? So this is a point of confusion. This is not a binary tree. A binary tree stores pointers, it creates nodes. This is not a binary tree. It's just an array of objects, but I'm going to interpret the array. And when I say like when we code it, when we think about it, when we want to analyze it, we interpret it as if it's a tree. But the storage is just as an array. Now, why in this way? So you see 1, 2, 3, 4, 5, 6, 7. Then I can do 8, 9, 10, 11, so on and so forth. Just write it out. So let me ask you a few questions. And by answering these questions, I think you will understand things a lot better. What is the parent of AI? Is it A of the floor of I over 2? Is it A of I minus 1 divided by 2? Or is it A of I minus n divided by 2, where n is the size? So which of these is correct? Look at the example and it will make sense. Right, so recall that the floor is basically rounding down. The floor is rounding down. Okay, so I think most of you see the answer. It's I over 2. So what's really nice about this is that you don't even need to follow pointers. If you simply take the index and divide by 2, round down, you get to the parent. Okay, now here's my next question. Let the root be at level 0. So I'm just going to assume that this is level 0, this is level 1, level 2, so on and so forth. How many nodes at level I? A level, I'll call it L. Okay, level L. Is it 2 times L? Is it 2 plus L? Or is it 2 to the power L? How many nodes at level L? Okay, good. So I think most people see that the size is 2 to the L, which again is not surprising. You know, it's a binary tree, so the sizes are all growing. The size, I should say, the number of nodes at each level is growing exponentially. Okay. Whoops, let's keep this. Now that you've, understood these, my next question is, if there are n nodes or objects in the heap, what is the maximum level? And this we can also call the depth. What is the maximum level? Is the maximum level going to be theta of n? Is it going to be theta of log n? Or is it theta of 1? Okay, good. So you all see that it's theta of log n. It's basically just log n maybe plus minus 1. And there are multiple ways of seeing this. One way to see this is by looking at this question. The number of nodes at level L is 2 to the L. So you sort of have to go up to log n levels before you can actually have n nodes. Another way is to actually look at this. You get to the parent by dividing by 2. And so if you start at an, how many times do you have to divide by 2 before you get to the root? And that's again going to be log n times. So it's the same math, but it's different ways of interpreting it. Any questions about this? Okay. So I also want to give you another interpretation. So I drew it as a tree, but let's go back and look at it as an array as before. So remember that the 0th node has nothing. So you have A1. Now, if you think of it, this is level 0, which has one node in it. This is, A2 and A3. This is all the nodes at level 1, right? So this is of size 1. This is of size 2. And then if you look at the next chunk of size 4, this is level 2. And then you keep going, level 3 are all the next nodes, and there are 8 of them, so on and so forth. So if you keep going, and let's just say that this is n here, right? So this is an, which is the last element that you're storing. So this is going to be present in some level, which is basically going to be like log n. That level is going to have these nodes. All these other levels are completely filled up except for the last level. Any questions? Any questions? Okay. All right. So far I haven't really done, I haven't really done anything particularly interesting. I've just taken an array and I have interpreted it as a binary tree. This doesn't tell us anything about how an operation like find max or extract max or increase key can be done efficiently. And it turns out that the main sort of the secret sauce of the binary heap is what's called the binary heap invariant. Now you will see this word pop up a lot when we talk about data structures and algorithms. Invariant is something that does not change. So it's a special property that the data structure has. So for example, in a sorted array, the invariant is that the array is always sorted, meaning that every element, is maybe less than equal to the next element, right? So that's an invariant. Now in a binary heap, we have a more stranger invariant. The invariant is that the key at the parent is greater than equal to the key at the child, right? So what this just means is that for all I, remember this is the symbol for all I, AI, the object at I, and I'm just going to use the key. I'm just going to say dot key to imagine that key is a field in it. AI dot key is greater than equal to A to I dot key, and AI dot key is greater than equal to A to I plus 1 dot key, where again 2i and 2i plus 1 are the children of I. So this is an invariant. We will maintain this property. So the question, which immediately when we look at this, question is which element has the maximum key? Is it A of 1? Is it A of n? Or is it something else? Which element has the maximum key given that these invariants hold? All right, so it seems that most of you see the answer. It's A1. Why? Because A1 is the element that is at the top of the tree, and the parents always have a higher key than the children. And so as you go up the binary heap, as you go up the tree, the keys cannot decrease. And hence, the max is at the root. But this sort of holds sort of inductively at every step. So A2 is going to have a key that's bigger than A4 and A5 and A6, not A6, but A7, not A7, I'm sorry, A8, A9, A10, A11. Let me draw an example. And so let me write something here which should hopefully be obvious. Find max can be done in theta of 1. It's sort of quite obvious because you can easily just find the maximum by just looking at what is the element, what is A1. But the problem is the other operations now become more complicated. Okay, so let me just draw a simple example of a binary heap, both of what it looks like as a heap and what it looks like as an array. Okay, so here's my heap: 42, 25, 7, 15, 3, 4. So this is a heap. When it's actually structured, and I'm only writing out the keys, not writing everything. So here's 42, 25, 7, 15, 3, and 4. Now, what's very important to note is that the array is not sorted. And in a heap, the resulting array doesn't have to be sorted. Actually, it will not be sorted. We do not make any claims about the values, the children of 25, comparing with these. So for example, 25 as a child of 15 is actually more than 7. So it's not that the values go down level by level. They go down only along a path. So I'm just sort of, here are the levels. All right, I want to emphasize this point and make it clear. This is not a binary search tree. This is not a binary search tree, right? All it is saying is that parents have a higher key than children, right? Somewhat like society. Parents dominate children, and that's it. The relationship between the two children, there's no guarantee. The invariant doesn't say anything about it. The invariant also doesn't say anything about, like, individuals and uncles or nieces or anything like that. Right? You could think of this as like, 7 is the uncle of 3, or the aunt. But there's no relationship there. It's because you have 15 and 7, you have 3 and 7. The only property is the heap invariant. This is the only property. All right, so I'm just going to put that in a box. Okay, so what is the issue? The issue is that inserts and extract max operations change the heap and destroy the invariant. Right? It destroys the invariant. So we need to fix this problem and restore the invariant. This is a very, very key concept in a lot of data structures and algorithms. This is the way that you actually think about it. This is like the science in computer science. So the way it works is you define an invariant. You say, oh, if my data structure had this property, then my operations become really easy. The find max becomes easy. Well, not all operations, the find max becomes easy. Now the problem is if you insert, so let's go ahead and insert something into the array, right? Let us insert a number, let's insert 30. So then what this would mean is you would put 30 over here. But that destroys the heap property. And so what we now need to do is we need to manipulate the data structure to make it have the heap property. We need to fix this. Okay, we need to fix the property. Now you could imagine fixing this by maybe shifting some of the values around. And so what we will do is we will formalize this. We will formalize this by a procedure called Heapify. Okay, so what Heapify is going to do is, so the way to think about this is, let's say you have your class heap. We're going to have some procedure Heapify in this class. Heapify is basically going to take, it's going to take a single argument. It's just going to take an index. So, if it's going to take, let's say, an unsigned int index as an argument. And so I'm going to write something here, and then I can explain, I'll explain it for a question. So Heapify assumes that the children or the child subheaps, so the child subheaps of index, satisfy the heap property So what this means is here's your heap somewhere. So here's your heap. And I is just some index somewhere. So this is A of I. Heapify assumes that these satisfy the invariant. What is the invariant? The heap invariant. And maybe I'll just write that. The heap invariant is simply that parents dominate children. And so that happens sort of under AI. But maybe it doesn't happen at AI. Heapify is going to fix that problem at AI. So Heapify will fix things so the subheap, so that the subheap rooted at index, sorry, instead of I should have called that index. So really A of index. The subheap rooted at index also satisfies the heap property or the heap invariant. Okay, when I mean property, I should also say invariant. Before I explain Heapify, and indeed the description of Heapify is not very hard to guess, I want to make sure that you understand what I'm trying to do here. I'm defining a procedure that has an assumption. Given that assumption, it will do a fix. Given the assumption, it will do a fix. So you can imagine that initially, maybe this bigger triangle, the bigger tree was not a heap, but the children were both heaps. So assuming that the children are both heaps, Heapify will fix the problem so that the tree rooted, this larger tree, is a heap. All right? Any questions? Any questions? And really, one way of thinking of it is what Heapify is going to do is it's going to push the problem down until it finally gets to the end and it gets resolved. So for example, in this example, it's kind of easy to guess how you would, so for maybe this is a useful example to have. If you call Heapify at 7 at the index, so the index 7, the index would be 3. If you call Heapify for this node, it satisfies this assumption because the children are both heaps, just trivially because a leaf by itself is a heap. But this structure here, the 7, 4, and 30 is not a heap. And it's not a heap because 7, the parent, does not dominate the child 30. So you would swap. If you swap the 30 and the 7, well, then you end up with a heap. And that's exactly what Heapify is going to do. It's going to swap parents with children. Okay. So let me write out Heapify, and I think then maybe some of this discussion will become clearer. Oops. Okay. So it's Heapify. Now I'm not going to carry around types. So I'm just going to say Heapify at index, and this is also called syncing. You'll see it's called syncing because low priority elements are going to go down the heap. And instead of writing it now as sort of code, I'm going to write pseudocode just with numbered lines because now I want to get to sort of talking about things at a higher abstract level. So I'll just say if A of I, sorry, instead of index, let me just call this I. It's going to be more convenient for me. If A of I is a leaf, well, then we're done. This is just the base case. So if A of I is a leaf, there's nothing to do because it's trivially a heap. Okay. If A of I dot key is greater than the maximum of A of I plus 1 dot key and A of, I'm sorry, not, my apologies, is greater than the maximum of A of 2 times I dot key and A of 2 times I plus 1 dot key, well, then we're also done because it's already a heap. Okay. So now this is where the real work happens. Okay. So maybe I should explain again. These are the leaves, right? These are the nodes with no children. The nodes over here with no children, these are leaves. So obviously, if you call Heapify at any one of these nodes, there's nothing to do because it vacuously is a heap because a leaf has no children. It dominates its children trivially.
There's a clarifying question. Are you referring to the addition, the insertion of 30, or the extract max procedure?
I'm sorry?
Are you referring to extract max or insert with Heapify?
Okay, so I'm kind of fudging here. I haven't actually told you how to insert or extract max. I'm actually telling you how to do Heapify. And I'm going to use Heapify to do the insert and the extract max. So
Heapify
right now, let's just say, suppose I inserted 30. To be concrete, let's say I inserted 30 and I let it be here. I'm going to call Heapify to fix things. Okay, so now suppose neither of these conditions hold, and this is where it gets interesting, I'm going to find the child of AI with larger key. And I'm going to call it J. Right, so J is either 2i or 2i plus 1, depending on how they compare. I swap AI and AJ. And then I just recursively call Heapify at J. Okay, so here's what I'm doing. I'm basically pushing the problem down. So let's, for a moment, let's ignore how this came about. But suppose you had a heap that looks like this. Right? It's not really a heap, it has a problem. And the problem, you could say, is at 7, because this is a subheap that doesn't satisfy the heap property. So you could call Heapify from this node to fix the problem. I haven't explained how you're going to find this node, where how are you going to detect the problem, so on and so forth. But just as an example, Heapify is a mechanism to fix the problem. So you see that when you have, so maybe I'll draw another picture here. Suppose you have any subheap, both of the children are heaps. The only problem is here. Everything else is a heap. So this node, which I've shaded is the root, might actually be smaller than this node. So this is the I and this is J. So what we're going to do is we will swap I and J, and then we might have, now once we swap I and J, so J goes there, whatever, maybe the index is bad, whatever value is here goes there, and whatever value object is here will go down there. Note that the left subtree has been preserved, nothing happened, so there is nothing to do there. But we might have a problem here because we just did a swap. Maybe this value is also smaller than this. Then it'll have to do another swap. So we just call Heapify recursively at the child.
Professor?
Yes.
All right. I'm a bit confused myself. It seems like you're inserting, which should be this swim procedure, but now you're talking about sinking downwards.
So, okay, yeah, so I ignore the insert, ignore whether I did an insert or an extract max. Maybe I shouldn't have done that. I'm just saying Heapify is just a procedure that does the following. Right? Heapify just does this. It assumes that the child subheap satisfy the heap property, and it fixes things so that the subheap rooted in the index will also satisfy the property. Is that any questions about that? Using Heapify, I'm going to show you how to do inserts and extract maxes. Now that we've done this, let me show how to do extract max. We will simply swap A1 with A of size being the last element. Decrement size. And we call Heapify at 1. Okay. So is that clear? So just to give you let's go back to our example heap. So it's 42, 25, 7, 15, 3, and 4. So sorry, let's ignore that insert of 30. So suppose this was your heap. right? And I'm drawing out the heap again over here. 42, 25, 7, 15, 3, and 4. How is this going to work? So we basically will, just like as we deleted in an unsorted array, we will swap 42 with the end. Remember, so size was pointing to that. We will swap 42 with there, so we could move the 42 over there. And then we decrement size. So size is going to move here. So that effectively deletes this. But now what we have resulting is not a heap any longer. If I look at what change it did there, so now 4 is going to be at the top. And this, of course, just disappeared. So this 4, 25, 7, 15, and 3 is not a heap. But this part is a heap. The left and right parts are heaps. So I call Heapify starting at the root. The 4 is going to swap with the 25. So it's going to come down. And then it's going to swap with the 15. So the 4 is just going to go down. That's why it's a sinking procedure. This is how you extract the maximum. Is this clear? Any questions about how the extraction is done?
So for the extraction, the root, which was 42, is the one that is extracted, right?
Exactly.
Or is it swapped with the last child?
Well, it's swapped with the last child, but extracting just means that you get it and you remove it from the heap. So you've decremented size, so now it's out of the heap.
Okay, I see.
Right? So you've decremented the size to basically get rid of it from the heap. So it's not in the heap any longer.
Right, okay.
I mean, it might be sitting in the array, but in some sense, it's only up to size that you're looking at the heap.
Okay.
Yeah?
Yeah, that makes sense.
Right? So extracting max is not just finding the max, because finding the max is easy. It's just the first element. Extracting the max is about basically removing it from the heap. Yeah. Any raised hands, go ahead and can unmute and ask your question.
Yeah, so I just had a question. When you extract the max, do you have to make sure the tree is even? So like you would put 4 back on the right side instead of putting it on the left. So you have an even number.
You don't have to, no, you don't maintain any of those conditions at all. The thing is, there's no rebalancing that is happening here because the structure of the tree is pretty much fixed. Like the children of whatever is here are these two things. The children of this is these two things, so on and so forth. Meaning, just to go back to, the structure of the tree is fixed. You don't maintain anything with like how many nodes are here versus how many nodes are there. For those of you who have seen trees and self-balancing trees, this is not going to do any of those operations. It's simply going to move whatever was the last element to there, and then that is going to now swim down. It's going to basically sink downwards using the Heapify operation to fix the heap. Is this clear?
Just to be clear, so it'd be correct if 4 went either to the left or to the right.
It would not be correct. Okay, so let's look at this example here. So I'm just going to draw 4, 25, 7. 15,
Oh wait, I see.
3. You see that 4 has to swap with the 25. It cannot swap with the 7.
Yeah, I see that.
So 4 is going to swap with the 25, which is going to swap with the 15. So, and that is what Heapify does, because Heapify just swaps it with the larger child. So on Heapify will lead to first the following, right? Because these two got swapped. And then 4 will swap with 15. So 25, 15, 4, and 3, and 7. Okay, so that's what it leads to. So this is how you do an extract max. Now note that, what is the running time of Heapify? What is the running time of Heapify? If you think about it, it's really just the depth of the tree because you're always swapping with children. And so the running time is O of log n. It is theta of log n, but I'm saying O of log n for a particular reason, which I'll come back to. But it's basically O of log n. It's log n, and the extract max is also going to be O of log n. Right? So in logarithmic time, you can extract the maximum. You can find the max. I haven't told you about inserts, and that I need to tell you. And this is alluded to earlier that there's a different procedure called swim, which is going to do that. But essentially, the idea is really quite simple. It's all about swapping parents and children to maintain this domination, to maintain the fact that the parent's key is always going to be larger than the children's key. Any questions about this? I'm going to pause here, maybe take like, a 2-minute break so everyone can take a breather. I will answer any questions that anybody has in the meantime.
Quick question, Professor.
Mm-hmm.
You might have went over this, but I might have missed it. How does Heapify detect which like where it's gonna swap or what needs a swap?
So good. So Heapify actually does not detect where there is a problem.
Oh.
It just says, so Heapify, it's kind of a funny procedure because it has an assumption and it will fix things assuming that the assumption is correct. But it only fixes things in a particular region.
Okay.
The important thing is you have to tell where Heapify should start. And in this case, you tell it to start at 1. And why is it that you can start at 1? Because you know that the children's subheaps, the children are already subheaps, right? Or rather the children's subtrees or the children's subheaps already satisfy the invariant because the only change you made was at the root.
Oh, yeah.
Now, if you made more changes, then Heapify will not be able to fix the problem.
Oh.
Right? So it's not like it will handle any problem. It only handles a very specific problem. And that is basically saying there is an issue with one node and it will fix that.
Okay, so you basically have to know where the problem is beforehand to know.
Exactly.
Okay, got it.
But what we will see is that the way we design the data structure, we will always know where the problem is because we only make a change at one node.
Yeah, makes sense.
Right? So we'll only make changes one node at a time so we know where the problem is. So every time there is a problem, we immediately will call Heapify to fix it. Or some equivalent thereof.
Cool, got it.
Okay. Any other questions?
Yeah, I had a question.
Yes.
So is it ever going, I'm assuming it's possible. So if we were to come across a binary heap that has, multiple problems with the invariant,
Mm-hmm.
so like, multiple levels of,
Mm-hmm.
so if we wanted to sort that correctly, we would call Heapify from the bottom to top, if I'm understanding that correctly. So that way the children heaps are correct, like in the assumption.
Excellent. You're getting ahead of me, but that is absolutely true. Yes. You're absolutely right. If you call Heapify in the opposite direction, starting from leaves moving upwards, then you can essentially fix all problems.
Professor, can you just pull up to the top of the page for the Heapify just for a second?
Yeah, sure. Let me actually zoom out a bit so that you can see the entire page.
To clarify, to fix everything, you start at the top or the bottom?
You start at the bottom.
But if it's a leaf, then you're just done.
Right, exactly. But then you fix the leaf, then you fix the parents of the leaves, then you fix the parents of parents, so on and so forth.
Oh, okay.
You cannot
Dies.
you cannot do it the other way around, because if you start at the top, the assumption of Heapify that the children satisfy the heap property is not true. But if you start at the bottom, then this assumption is true. So yes, that's absolutely true. But that is jumping ahead about towards the end of what I wanted to say. But that is absolutely true. Okay, any questions about Heapify? Yes.
If you had like, let's say the children were both the same value, and those values were both more than the parent, which one does it matter which one you choose to heapify?
No, that's a good point. So if both of them had the same value, then you can pick either of them.
Okay.
And that's because the heapify property, as stated, usually has a greater than equal to. Sometimes when it comes to coding these things, this can be a bit of a pain. So what they will often do is they will break ties in some way or the other. Because if you assume that this is actually some object, then you might use some other attribute of the object to break the ties. But that's more of an implementation detail. But you can use either of them, and they're both correct. Okay, good. So I think that hopefully most of you have followed this. And on the course website, I have a link to a visualization. It's a very nice visualization that I found online. This is by someone else, and the link is there. And you can actually like insert into the heap, and you can play around with it. And it's an excellent way of understanding a heap even better. Okay, so far we've done extract max, and now we need to do inserts. So now let's go back to our example, the one that I had. 42, 25, 7, 15, 3, 4, and I had inserted 30. Now, as many of you would have guessed, the way to fix this problem is actually quite easy. You swap the 30 with the 7. Right? So you can easily convert this to the heap just by swapping the 30 with the 7, and everything else is just going to stay as is. So let's try to formalize this procedure. So the way we'll formalize it, and this was alluded to in a comment that Mohammed had, that I'm going to define another procedure. And essentially, there's a procedure called swim, which is also going to take in an index. So one way to think about swim is that now Heapify had this assumption that the children satisfy the heap invariant, and the Heapify will fix things so that subheap also satisfies the problem. So you have localized the problem to a particular node. You're ignoring everything else above it, and you're only looking at the things below it. In swim, what is going to happen is that it's sort of the opposite. So let me just describe the procedure, and then you'll see what's going on. And you can easily see that if it was not 30, but it was 300, then the 300 swaps with the 7, and then the 300 will swap with the 42. Right? They would just go up. So this is called swimming, whereas the previous was sinking. So in swimming, high priority items swim to the top. In sinking, low priority items will sink to the bottom. So what one has here is one again says if I is equal to 1, then return. This is going to be the base case. If AI dot key is less than AI divided by 2 dot key, return. So there's no problem. Otherwise, you swap ai with a of I divided by 2, and then you just call swim at the parent. So what is swim assuming? One way of thinking about swim is that, so A is a heap, but there may be a problem with I and its parent. In the previous, in Heapify, there may be a problem with I and its children. Here you're assuming that there's a problem with I and its parent. So another way of interpreting this is that we'll assume that the subheap rooted at I is a heap, or the subtree is a heap. The subheap rooted at I's sibling is a heap. But the subheap rooted at I's parent may violate the invariant with I. Right? That's sort of the assumption. And so what the swimming procedure does is it will fix that problem. And so again, if you think about it, it's a recursive procedure. It makes one recursive call, halving the value of the index. And this again runs in O of log n. The insert now becomes quite simple. Once you have the swim procedure, you have an insert. So if you want to insert an object, what you do is you simply increment the size. You set a of the size to be equal to the object, and then you call swim at size. And again, this will run in O of log n. Okay? So this completes the basic description of the heap. There are a few more things that I will talk about building a heap and sorting with a heap. But any questions about this?
I had a question.
Mm-hmm.
So when you insert, wait, sorry, I just forgot about it. Let me gather my thoughts again. Sorry.
Sure.
Oh yeah, so to insert, you would swim, but then to extract the leading term, you would heapify.
Exactly, which is a syncing operation, right?
Yeah.
Because Heapify is kind of pushing things. So some people call it sink and swim. Like there's a swim and usually Heapify is often called a sink. The reason that I use the term Heapify is because that's what's used in CLRS, which is commonly used. It's a good reference to have for this, and that's why I have this way of describing it.
Thank you.
But you can have a sink and a swim, which is maybe another common description of it. Right? So the extract max, the extraction. So you can think of it as what happens is, maybe one way to describe it is the extraction creates a problem with the root, which needs to be pushed down. The insertion creates a problem at a leaf, which now needs to be pushed up. So there is the visualization. I also have an implementation of a heap that I will provide as a Codio box, so you can play around with it. And indeed, there's some functions in that I have not implemented, and that will be, part of, that will be a test question for test 3, not test 2. But are there any questions? It's actually, it's really clever. It's very neat, right? That you can get all of these operations basically in logarithmic time, right? And no pointers. It's just maintaining an array. But it's sort of cleverly come up with this invariant so that if you maintain the invariant, then the operations are quick. They run in logarithmic time. Any questions?
Could you possibly clarify that you said if you call Heapify on the end of the heap, you can fix the whole heap?
Okay,
per se?
so yes, good. So I'm gonna come to that.
Okay, because I was wondering how that doesn't violate rule 1, that if it's a leaf. That's what I'm confused about.
Rule, I'm sorry.
Sorry, of step 1 of Heapify, which is if AI is a leaf done. How does that not violate that?
No, so essentially what's going to happen, okay, so let me come to this. I'll come to this shortly. Indeed, that's a good segue into what I wanted to say. So, okay, so given all of this, sorry. Now here's something that you may not have seen, although many of you have probably have heard about merge sort and quick sort as n log n time sorting algorithms. You can use heaps to sort, and it's called Heapsort. So the first step is insert all elements of A into a heap, which is essentially convert A into a heap. And then what you simply do is run extract max n times, and essentially just output A. So what's going to happen is, if you think about it, when you convert it into a heap, when you do the extract max, it basically swaps the heap with the end and then decrements size. But the last element is still going to be there. When you run an extract max again, it's going to move whatever was the maximum to here and then decrement size, so on and so forth. So when you run extract max n times, you end up with a sorted array. So this is n inserts. This is n extract maxes, and the total runs in O of n log n, because there were n inserts, each being n log n extract maxes, each being n log n. Right? So this is a very neat sorting algorithm, and this is actually a pretty important concept, that now heap sort, unlike the quadratic time, heap sort sorts arrays in O of n log n worst case time. And this is another important running time. It's technically theta of log n, which is more complicated to say why it's theta of log n, but just like you saw linear time, constant time, quadratic time, logarithmic time, there's n log n time. Another very important sort of friend that we see whenever we study running times. So this is heap sort. Any questions about heap sort? Okay. Now I want to talk about this first step a little bit more. This is a particular operation which is called the build heap operation. Build heap is to essentially convert an array into a heap. So what you could do is, given any array, imagine, given an array A, imagine A is a heap, but potentially violates the heap invariant everywhere. Right? Potentially it actually violates it everywhere. So far all the discussions that we've had are that the heap problem is in one place, but if you wanted to build a heap, if you just think about your array, the problems could be everywhere. And as was mentioned, again, there is a very clever way of doing this, of building a heap. And how do you do build heap? So let's just say that A has elements from A1 to AN. So the indexing is off by 1, but as we discussed, that would make things easier. So we'll say for I from N to 1 in reverse order, just call Heapify of I. And this is going to build a heap. Okay, so why is that? Let's go back and suppose this was just some completely arbitrary array. 42, 103, 9, 57, 200, 36, 40. Right, so this is clearly not a heap property. How would we call Heapify? So we would start in reverse order. So we know that this is a heap by itself. So Heapify is just going to, when you call Heapify on this index, it just returns. You call Heapify on this index, it returns. Call Heapify there, it returns. Call Heapify there, it returns. Now you call Heapify here. Why can you call Heapify there? Because you know these are heaps. It's going to, what it will do is it will swap with the 40. So it's going to make that 40. 36, 9. Then it's going to go there. It's going to call Heapify on that. So you know that these are heaps. So Heapify will work. And Heapify will put the 200 over there. 57, 103. So now this is a heap. And this is a heap. So we go here and we call Heapify at the root. And as we know, that's going to fix the problem. And we'll end up with a valid heap. So when you call Heapify in reverse order, it makes everything into a heap. Is this clear?
So basically you're just iterating through each leaf and just calling heap. Is that what you're doing?
Not just each leaf, each element.
Oh, each element. Okay.
But in reverse order.
I see.
Because if you call Heapify, let's say you started with this and you call Heapify at the root, you have a problem. It's not going to fix the problem. Now the reason is, okay, so let me give you an example where it's not going to fix the problem. So let's just say that instead of this, I'll give a different example. Let's say this is 190. Okay? And you call Heapify on this. Observe that 42 is going to swap with the 190. But actually, it should have swapped with this so that it can get the 200 up there. But because this is not a heap, it's not going to work. I hope this example makes sense. If you call Heapify on 1 in this structure here, you call Heapify on 1, you will not fix the problem. Indeed, you're going to end up with the problem yet again. It's just that because the 42 will swap with the 190. So 190 is going to end up over there. But you actually want 200 to get up there. So if you call Heapify in the opposite order, then by the time you call 42, the 200 has already come up. Any questions about that?
Since Heapify only swap 2 elements, and for example, the 9 is swapped with is first swapped with 36, but 36 is still smaller than 14, so we have to do this Heapify process on the swap 36 again, right?
So Heapify doesn't do one swap. Heapify does multiple swaps. Because Heapify is a recursive procedure. Heapify does one swap, but then it recursively calls itself. So it can do multiple swaps.
Okay.
Right? So the way to think about this is to go back to this example where this was a 9. Sorry, I'm just going to get rid of that, make it a 9 again. The 9 swapped with the 40. So there was no problem with 36 any longer because the 40 went up and there was no problem any longer. The problem is only that the 42 has to swap with, the 200 and move down. Any other questions? If there's any
So
raised...
in the initial heap, wouldn't 42 have to go down and swap with the rest?
You mean in this?
Yeah.
So the thing is, you cannot call Heapify on 42 when you start with the left.
Oh, because it's already assumed that it's following the conditions of the heap.
Because the children don't satisfy the heap condition. Heapify
So you have to work your way upwards.
Exactly. Heapify only works if the children heap satisfy the heap condition.
I see.
Right? So you just call Heapify in opposite order and it works.
Could I ask you what it looks like if you were to write that heap into like in an array format, but then what it looks like when we traverse that array in a recursive order?
I'm sorry, say that again.
If you were to rewrite that tree, but like in the array format, and then what does it look like when you call a recursive function? Just which index? It's just going to go from right to left. Is that
exactly?
That simple?
Exactly. It's just going right to left.
Okay.
Precisely.
Okay.
Yeah, you're right. It's just going to go in this order, right? It's just going to go all the way back.
Okay.
It's I don't know. It's almost magic. Right. It's almost magical that all of this works out, and it's all just log n. There's another bit of magic here, which clearly I cannot explain everything in the next 3 minutes. But what is the running time of this procedure? So can someone say, okay, what is the running time? You'd say the running time is O of n log n. Why? You say n calls to Heapify. Turns out this is not the best you can do. We can prove it runs in linear time, O of n time. And it's actually theta of n time. But the proof is more complicated because the thing is, it turns out the Heapify calls at the bottom are actually much faster than log n. It's only the Heapify calls at the top that are taking time. The Heapify calls at the bottom are actually quite quick. And so if you kind of carefully do the math, you can prove that build heap runs in linear time. And this is again, this is like a nugget on heaps that sometimes, people test on in interviews. How long does it take to build a heap? And you'd say, oh, it's n log n because you have to do n inserts. The answer is no, you can actually do it in linear time. But then, of course, the extract maxes are going to will take log n. So heap sort will still take n log n. But the building of the heap in this way, when you do it in reverse order, only takes linear time. The intuition for that is that the Heapify calls down here, Heapify runs faster than log n steps. And the math is given in CLRS, and I can do it, but will take more than a few minutes. And so at this point, I will just leave you with this fact. So I've covered a lot of ground today. I've talked about binary heaps, and I'm going to end the discussion on binary heaps with this. What is important for you to know again is, sort of going back to the beginning, binary heaps are a data structure that can implement priority queues very efficiently. It implements the ADT priority queue by doing inserts, extract maxes, increase keys. All of these operations can be done in logarithmic time. And the key are one can think of it as sinking and swimming, which one procedure is called Heapify, which does the sinking. And the sinking fixes the problem at the root. Whenever you delete, whenever you extract max, you have a problem at the root. Heapify fixes that. When you do an insert, you have a problem at a leaf. That is fixed by the swim operation. And if you put it together, then you can do all the operations in linear time. Heapsort is an O of n log n time algorithm that does sorting. And sort of an additional nugget is that a heap can be built in linear time faster than n log n by doing Heapify in this opposite order. I will share with you my implementation of a heap, and hopefully that will help you clarify things. So I'll end now and take any questions that you have.